Today I am going to discuss overdispersion in logistic regression. Logistic model yi follow binomial ni pi I independently. Where pi I equal to e to the power xi curl beta curl by exp by 1 plus exp xi curl prime beta curl, where we consider k explanatory variable and beta curl equal to beta naught to beta k and xi curl x naught x1 xk prime x naught equal to 1. So since yi follow binomial ni pi I, then expectation of yi which is equal to ni pi I and variance of yi equal to ni pi I 1 minus pi I. If one assumes that pi I is correctly modeled, but the observed variance is larger or smaller than the expected variance from the logistic model given by ni pi I 1 minus pi I, then one speaks of under or over dispersion in application, one often observes only overdispersion, so we concentrate on modeling overdispersion. Next, how to detect overdispersion. If the logistic model is correct, the asymptotic distribution of residual deviance D which follow chi-square n minus k degrees of freedom. Therefore, expectation of D equal to n minus k. So, if D, observed D greater than degrees of freedom, this is the degrees of freedom of the distribution of D. So if this observed D greater than n minus k, then one can, but it can indicate overdispersion. So the rule is, if your observed D is greater than n minus k, that is the degrees of freedom of the distribution of residual deviance, then we say that this model suffer from overdispersion. So, or other way you can say that observed D divided by n minus k greater than 1. These are same thing. But the warning is, suppose you get D greater than n minus k, this thing can also be happen due to some other fact. One, if some covariate values are missing, that is missing covariates, and or interaction terms another may be due to negligible or negligence of non-linear effects, or you may use you use wrong link function, or existence of large outliers. And lastly, binary data or your NI is very small. So the D greater than n minus p can also be result, that is, one is missing covariate and or interaction terms, negligence of nonlinear effects, wrong link function, existence of large outliers, binary data or Ni small. These are the reason for which D greater than n minus k. So please, when you conclude that your model is suffered by overdispersion, then you also think about this. So for excluding this reason, so detecting whether the model suffering from this reason means missing covariate, negligence of nonlinear effects, wrong link function, existence of large outliers, binary data or Ni small, so we need EDA, that is explanatory data analysis, exploratory data analysis, and regression diagnostic. Next, the reason for overdispersion. Overdispersion can be explained by one, variation among the success probabilities, or correlation between the binary responses. These both reasons are same, since variation leads to correlation and vice versa. Now consider a example where this thing happened. Suppose that an experiment exposes pregnant mice to a toxin, and then after a week observes the number of fetuses in each mouse's litter, that show signs of malformation. So we consider an experiment exposes pregnant mice to a toxin, and then after a week observes the number of fetuses in each mouse's litter that shows signs of malformation. Let small ni denote the number of fetuses in the litter for mouse eye. The mice also vary according to the mice also vary according to the mice also vary according to other factors that may not be measured. Such as weight, overall health, and genetic makeup. Extra variation then occurs because of the variability from litter. extra variation then occur because of the variability from liter to liter in the probability pi of malformation. The distribution of number of fetuses per liter showing malformations might cluster near 0 and near ni, showing more dispersion than expected for binomial sampling with a single value of pi. Overdispersion could also occur when pi varies among fetuses in a litter according to some distribution. Another example, the difficult now we consider another example, example 2. The default probabilities of a group of creditors with same condition can vary from bank to bank. Reasons for this cannot be measured or imprecisely measured covariates that make groups differ with respect to their default probability. So these two are two examples where this overdispersion situation occurred. Now suppose yi equal to sum over j from 1 to ni uij, where uij equal to 1 for success, 0 for failure. Then we know variance of yi, which is equal to sum over j from 1 to ni, variance of uij, since within a group uij, that means given I, uij and uij dash are not independent, so j not equal to j dash ni of uij comma uij dash. Since this portion is not equal to 0, so variance of yi should not be equal to ni pi I 1 minus pi I. This is the variance when this is the situation when over dispersion or under dispersion does not occur. That means when variance yi follow binomial distribution ni pi I, then this is the variance. But if uij's are not independent, then the variance of yi not equal to ni pi I into 1 minus pi I. So this is a binomial variance, ni into pi I into 1 minus pi I. Hence yi has not a binomial distribution. This situation occurred when same patient is observed over time. Another practical example when this situation occurred, that is all units are from the same family or little, that is cluster family. So the next issue is modeling when yi has not a binomial distribution. So modeling of variability among success probabilities. So our yi is number of successes in any trial, that is number of successes in any trials with random success probability vi से So now the issue is, now this is the thing, the success probability is random, that is Vi instead of pi I, and we assume that expectation of Vi, which is equal to pi I, and variance of Vi equal to phi into pi I 1 minus pi I, where variance of Vi equal to pi phi I 1 minus pi I. This phi is a known, this phi is a unknown scale parameter. Unknown scale parameter. Note that variance of Vi equal to 0 when pi I equal to 0 or 1. So Vi belonging to open interval 0 to 1 is unobserved or latent random variable. Now the conditional expectation of Yi given Vi, this is equal to nothing but Ni Vi, and variance of Yi given Vi, which is equal to Ni Vi 1 minus Vi. So this implies expectation of Yi equal to expectation Yi equal to expectation Yi given Vi equal to expectation Ni Vi, that is equal to Ni expectation Vi, which is equal to Ni pi I. Now variance of Yi equal to variance of expectation Yi given Yi given Vi plus expectation variance Yi given Vi. So this is equal to variance expectation Y given Vi is nothing but a variance Ni Vi plus this is equal to variance Ni Vi, variance Yi given Vi equal to, since Ni Vi into 1 minus vi. So this is equal to variance ni into vi 1 minus vi. So this should be expectation, sorry. So this is equal to ni square variance of vi plus ni vi minus vi square. So this is equal to expectation vi. Expectation vi square is nothing but a variance of vi plus e square vi. So this is minus variance of vi minus e square vi. So this is nothing but a pi I 1 minus pi I. So this is nothing but a pi into pi I 1 minus pi I. So this is equal to ni square phi pi I 1 minus pi I. Similarly, this is ni into expectation vi is nothing but a pi I. Variance of vi is ni. Variance of vi is phi pi I 1 minus pi I, and this is minus pi I square. So if you ni pi I into 1 minus pi I equal to ni phi plus one minus phi, and we get variance of yi equal to ni pi I 1 minus pi I 1 plus ni minus 1 phi. So if phi equal to 0, this implies variance of yi equal to ni pi I 1 minus pi I. So that means no over dispersion if phi greater than 0. This implies over dispersion. Phi and phi greater than 0, this implies over dispersion, provided ni should be greater than 1. If ni equal to 1, that is for Bernoulli data, no information about phi available, so this model is not useful. Now, modeling of correlation among the the binary responses yi equal to j from 1 to ni uij, where uij takes two values, either 1 or 0. When 1 it is a success and 0 when it is a failure, and probability of uij equal to 1 pi I. So this imply expectation of eij equal to pi I, but correlation between uij comma uij dash is delta, where j not equal to j dash. Then covariance between uij dash, which is equal to delta pi I into 1 minus pi I. Therefore, variance of yi is equal to ni pi I 1 minus pi I 1 plus ni minus 1 delta. Use the formula of summation j from 1 to ni variance of uij plus j not equal to j dash cob uij comma uij dash. Then you get this thing. Please check. Here also we see that when delta equal to 0, this imply no overdispersion. Delta greater than 0 imply overdispersion. If ni greater than 1, delta less than 0 imply under dispersion. Since we need 1 plus ni minus 1 delta greater than 0, so delta cannot be too small. For ni tending to infinity, delta greater than equal to 0. Again, we can check that unconditional mean and variance are the same if delta greater than 0 for both approaches. Both approaches means that is modeling of correlation among for binary response and modeling of variability among success probabilities. So these two things, modeling of variability among success probabilities and modeling of correlation among the binary responses, these two are same thing. So we conclude that these two approaches, that is modeling of correlation among the binary responses and modeling of variability among success probabilities, these two approaches cannot distinguish each other. So these two are same, which I already mentioned earlier. So now the issue is, so whether you use delta or phi, no matter. So we use general notation, that is phi. So now the problem is to estimate unknown phi. Now our yi given vi, this is follow binomial ni comma vi, where our vi expectation of vi equal to pi I, which is random. Vi is a random, and variance of vi, which is equal to phi pi I into 1 minus pi I. And suppose we consider G group, so I varies from 1 to G. Suppose ni equal to small n, that is balanced case. The number of observation, that is number of observation under each group, are same. Therefore, this implies variance of capital Yi, which is equal to n pi I 1 minus pi I into 1 plus n minus 1 small phi. And this is the, we take it as sigma square, and this is a heterogeneity factor so one can show that expectation chi square approximately equal to G, number of group, K is a number of parameters, K is a number of parameters in the largest model to be considered into 1 plus n minus 1 phi. So this is equal to G minus K, since we assume this is a sigma square, which is a heterogeneity factor, into sigma square, where this chi square equal to this factor I already defined in my previous video, I from 1 to small g small yi minus pi n pi I hat whole square divided by n pi I hat 1 minus pi I hat. Therefore, this implies sigma hat square equal to chi square g minus k, since sigma hat square nothing but a 1 plus n minus 1 phi hat, so this implies phi hat equal to sigma hat square minus 1 n minus 1. Note that estimation of beta in this case, that is the overdispersion situation, is same as the situation where no dispersion occur, no overdispersion occur. So this is the point. You also check this thing. Estimation of beta is unchanged. Now the next point, now analysis of deviance when variability among the success probability are present. So model degrees of freedom, deviance, so model degrees of freedom, deviance and covariates. For model 1, suppose degrees of freedom is gamma 1, deviance capital D1. For ith observation, the covariate values are xi1, xi2, xi gamma 1. For model 2, degrees of freedom gamma 2, deviance statistics D2, and the covariate values corresponding ith observations are here. For model 1, we consider only gamma 1 covariates. For model 2, we consider gamma 2, which is greater than gamma 1 covariates. So this should be like that, and this is the reference model. So here I use gamma naught covariate, I denote this D naught. So for yi given vi, this is follows binomial ni comma vi, I from 1 to small g, since we use G groups, since expectation chi square, this is approximately equal to sigma square g minus k. So we expect that chi-square statistics follow asymptotically sigma square into chi-square g minus k. So deviance statistics D follows chi-square g minus k into sigma square. So this thing imply D equal to d2 minus d1, sorry, this should be d1 minus d2 by gamma 2 minus gamma 1 d naught by gamma naught. I think it should be d2 minus d1. Sorry, this should be d2 minus d1 by gamma 2 minus gamma 1 divided by d naught by gamma naught. This follow asymptotically F distribution with degrees of freedom gamma 2 minus gamma 1 comma gamma naught. Hence no change to ordinary case. So this is similar as ordinary case. But standard error in the situation of overdispersion, this is equal to sigma hat into standard error, estimate of the standard error of beta j of ordinary case. So this is overdisperse and this is ordinary model, that is when ordinary means no overdispersion situation arises. This holds, this is because since we know variance of yi, this is equal to sigma square ni pi I into 1 minus pi I. We already proved this thing. So this part is nothing but a variance of yi for ordinary model, and this is the additional part. So using this fact we get this one. Here I mentioned that the expectation yi remains same as ordinary model, that is expectation of yi equal to pi I. So expectation of yi equal to pi I for both the cases, that is ordinary model and over dispersed model, both the situations expectation yi equal to pi I. Now we consider two approaches, one beta binomial model and another is Cauchy likelihood estimation to solve this problem. First I discuss beta binomial model. The beta binomial model is a parametric mixture model that is another alternative to binomial, that is another alternative to binary GLM with normal random effects. As with other mixture model, that assumes a binomial distribution at a fixed parameter value, the marginal distributions permits more variation than the binomial. Thus, a model using the beta binomial is a way to tackle or handle over dispersion occurring with ordinary binomial models. Let Vi, we already mentioned Vi is a Latin success probability that belongs to 0 to 1. We assume this Vi follow beta ai comma bi, then f Vi equal to 1 by beta ai comma bi, Vi to the power ai minus 1, 1 minus Vi whole to the power bi minus 1, where ai comma bi, this is greater than 0. And this is a, sometimes we denote this b instead of beta. So b ai comma bi is nothing but a gamma ai gamma bi divided by gamma ai plus bi. Now expectation of Vi, this is equal to ai by ai plus bi. So this equal to pi I, and variance of Vi, which is equal to ai bi by ai plus bi whole square, ai so variance of Vi, this is equal to ai bi by ai plus bi whole square into ai bi plus 1. Now I write this as pi I 1 minus pi I into tau I, where this tau I is equal to 1 by ai plus bi plus 1. If ai greater than 1 comma bi greater than 1 for all I, we have unimodality and variance of Vi, this should be less than pi I into 1 minus pi I by 3. Check. If tau I equal to tau, the beta binomial model is equivalent to the model with variability among success probabilities with phi, which is equal to tau, less than 1 by 3. So this is more restrictive situation. Now marginal likelihood this is equal to L beta curve I from 1 to small n integrate over 0 to 1 f yi given vi, which is a binomial distribution with parameter ni vi into a vi dvi. So this is equal to product of I from 1 to small n 0 to 1 ni cyi vi to the power yi 1 minus vi to the power ni minus yi into 1 by beta ai comma bi 1 minus into vi to the power ai minus 1 1 minus vi to the power bi minus 1 dvi. And if you simplify this thing, then you get product of I from 1 to small n ni cyi into beta yi plus ai ni minus yi plus bi by beta ai bi, where pi I equal to, as you know, e to the power xi curl beta curl by 1 plus e to the power xi curl prime beta curl ai by ai plus pi, because I denote pi I equal to pi I is a expectation of vi, not vi. Sorry, this is mistake. So correct form is this. So now the problem is to maximize to be maximized to determine Emily of beta curl. So for finding the Emily of beta curl, you need to maximize this, but the problem is that no standard software exists to solve this problem. Next, estimation in logistic regression with random effect. Suppose Zi, this follow normal 0 1 IID I from 1 to small n, then the joint likelihood for beta gamma Zi is given by L beta gamma Zi equal to product of I from 1 to small n, Ni Vi, Ni Yi, Ni Cyi, Vi to the power Yi, 1 minus Vi to the power Ni minus Yi, and this is equal to product of I from 1 to small n, Ni Cyi. Since Vi is nothing but a e to the power xi curl beta curl plus I think it is better to write instead of Vi. Okay, no problem, given a Vi, suppose. So this is nothing but a e to the power xi curl beta curl plus gamma Zi divided by 1 plus exp xi curl prime beta curl gamma Zi. So then this portion is equal to, this is whole to the power yi and this is whole to the power ni. So there is k plus 1 plus small n parameters. So this is a too many parameters. Therefore, we need to maximize the marginal likelihood, that is L beta gamma integrate over Rn L beta gamma Z fz dz. Since this fz, so you know this form L beta gamma z, which is nothing but a exp xi curl beta curl plus gamma zi whole to the power yi divided by 1 plus exp xi curl prime beta curl gamma zi whole to the power ni into, this is nothing but a root over 2 pi, since zi follow normal 0 1s, so 1 by root over 2 pi exp minus z square by 2, so write it this here, and it is zi, so 1 by root over 2 pi exp minus zi square by 2 the zi. This can only be determined by numerically. One approach is to use a Gauss Hermite approximation given by integrate over minus infinity to plus infinity fu e to the power minus e square du, which is approximately equal to sum over j from 1 to m cj f is j for known cj and sj, and for the values of cj and sj you can use Abramovich and Stigam table in 1972, and m approximately 20 is often sufficient. Here m approximately equal to 20, which is often sufficient, and you can use Markov chain Monte Carlo method, MC method, for solving this. Point to be noted, random effects might be correlated in time or space when time series or spatial data considered. Next, Cauchy likelihood estimation. Cauchy likelihood estimations assumes only a mean variance relationship rather than a specific distributions of distribution for yi. It has a link function and linear predictor of usual GLM form. That is, it has a link function and linear predictor of the usual GLM form. But instead of assuming a distributional type for yi, it assumes only variance of yi equal to v nu. This is nu mu I for some chosen variance function v. For some chosen variance function nu, the equations that determine Cauchy likelihood estimates are uj, that is corresponding to beta j, uj beta curl sum over I from small n, total number of observations, yi minus mu I, nu mu I, partial derivative with respect to partial derivative of mu I with respect to eta I equal to 0, where j equal to 1 to p, where mu I equal to g inverse sum over j from 1 to p beta j xij, and link eta I equal to theta I sum over j from 1 to p xij beta j. Note that they are not likelihood equation. However, without additional assumptions that yi has distributions in the natural exponential family. Note that Cauchy likelihood estimates have asymptotic covariance matrix of the same as GLM, that is x prime w hat x whole inverse. Overdispersion for binomial GLMs and Cauchy likelihood. The Cauchy likelihood approach can also handle over dispersion for count based on binomial data. Recall variance of yi, which is equal to variance of pi I, this should be nu of pi I according to the notation of Cauchy likelihood is equal to ni pi I 1 minus pi I into 1 plus ni minus 1 rho. Rho is a correlation. This is correlation model, same as over dispersion model. These two are same thing I already mentioned. So rho should be lies between minus 1 to plus 1. Here we assume that common correlation rho between each pair of the ni individual binary random variables that sum to yi. I again repeat this thing. Here we assume that common correlation rho between each pair of the ni, individual binary random variables that sum to yi, that sum to yi. The ordinary binomial variance results when rho equal to 0. So when rho equal to 0, this is nothing but an ordinary binomial variance. And for overdispersion situation, this rho should be greater than 0. For this Cauchy likelihood approach, Williams in 1982 gave an iterative routine for estimating beta and the overdispersion parameter rho. He let rho hat be such that resulting Pearsonian chi-square that sums the square deviation or residuals. So actually I want to repeat this thing again. Let rho hat be such that the resulting Pearson chi-square that sums the squared Pearson residual for this variance function equals the residual degrees of freedom for the model. This requires an iterative two-step process, and the first step is step 1, solving the Cauchy likelihood equation for beta curve for a given rho hat, and then step 2, using the updated beta curl hat, solving for rho hat in the equation that equates chi-square, which depends on beta hat curl and rho hat to its degrees of freedom. An alternative Cauchy likelihood approach uses the similar variance function nu pi I, which is equal to phi ni pi I 1 minus pi I so overdispersion occurs when phi greater than 1, when pi greater than 1, phi greater than 1. Then the Cauchy likelihood estimates are the same as ML estimates for the binomial model, since phi drops out enters the denominator of Wi, which is ith diagonal element of capital W. Thus, the asymptotic covariance matrix multiplies by phi and standard errors multiplies by root over phi. An estimate of phi using chi-square fit statistic for ordinary binomial model is, that is, phi hat equal to chi-square by n minus k, that is degrees of freedom, where chi-square equal to Pearson fit statistic for the binomial model. A plot of standardized the standardized residual for the ordinary binomial model against the indices Ni can provide insight about which is more appropriate. When the residuals show an increasing trend in their spread as Ni increases, the beta binomial type variance function may be more appropriate. This is because when the beta binomial variance holds the residuals from an ordinary binomial model have have denominator that is progressively too small as Ni increases. The two Cauchy likelihoods likelihood approaches are equivalent when Ni are identical. Only when the indices vary considerably might results differ much because the variance function nu pi I is equal to phi ni pi I 1 minus pi I has a structural problem when ni equal to 1 and has less direct motivation. We prefer Cauchy likelihood with the beta binomial variance function. I already mentioned in my video part 2 logistic regression, model building strategies in logistic regression using R, that when overdispersion situation arises, we cannot use binomial family. In that situation, we use Cauchy binomial instead of binomial. Other things are same. So this is GLM function. I consider plant plus MIGR plus dot dot dot, then data equal to capital data. Please see this video 2, model building strategies in logistic regression using R. And family, you write Cauchy binomial, instead of binomial, and other things are same. So this is the part where the over-dispersion situation arises. Next we will discuss missing value situation. So please stay with us. Till then, we will come back very soon with new video where we discuss missing data in particular this model, that is logistic model. So till then, thank you.